The research paper presents a novel approach for cross-domain policy transfer in autonomous agents, focusing on learning a shared latent representation across domains and a common abstract policy. The method leverages multi-domain behavioral cloning and maximum mean discrepancy (MMD) regularization to encourage cross-domain alignment. This approach does not rely on exact cross-domain correspondence and translation, instead learning a shared latent representation and a common policy. The method is compared to existing methods that rely on adversarial generation, showing its effectiveness in scenarios where exact domain translation is challenging. The paper also discusses related work in unsupervised domain adaptation, distribution matching, and correspondence learning, highlighting the importance of matching feature distributions between domains. The authors propose an algorithm consisting of two phases: alignment and adaptation, where the alignment phase involves training all modules of the policy via behavioral cloning and regularization terms, and the adaptation phase updates the common policy built on a fixed representation space to adapt to the target task. This paper presents a novel approach to aligning state representations across different domains and tasks using multi-domain behavioral cloning (BC), with maximum mean discrepancy (MMD), loss and temporal cycle consistency (TCC). The authors aim to learn a shared latent space for state representations that can be used across various domains and tasks without requiring domain-specific state information. The proposed method involves training a network with a state encoder, common policy, and action decoder, leveraging a combination of BC loss, MMD loss, and optionally TCC loss to shape the aligned representation space. Experiments on a maze environment demonstrate the effectiveness of this approach, showing that it can obtain a shared latent space that keeps the original structure of the state representations. Comparisons with discriminative training reveal that MMD is more suitable for achieving modest alignment while preserving the original structure of the latent space. The research also focuses on lifelong learning agents, introducing the portable latent policy (PLP), which updates the common policy on top of an aligned latent space. The adaptation phase can be done solely in the source domain using reinforcement learning, freezing the encoder and decoder weights during the process. Experiments evaluating the alignment quality and the method's ability to achieve zero-shot cross-domain transfer across various settings show that the regularization terms of PLP enhance the alignment quality, with the BC term significantly contributing to the alignment. Comparisons with baselines such as gamma, CDIL, and contextual policy highlight the effectiveness of PLP in achieving better alignment and transfer performance. The authors introduce PLP, a novel method for cross-domain policy transfer, leveraging implicit representation alignment of multi-domain behavioral cloning. PLP outperforms existing methods in most settings, achieving comparable or better performance than baselines. The authors investigate the effect of each loss term, finding the MMD loss enhances performance, while the contribution of task-consistent constraints is task-dependent. They also visualize latent state distributions, demonstrating MMD loss aligns representations while preserving structure. The ablation study shows PLP disk performs lower in environments with large domain discrepancy, and the BC-only variant achieves comparable performance but fails to adapt to highly OOD tasks. The authors identify limitations, including unstable performance and failure to adapt to complex OOD tasks, and propose future work directions such as combining PLP with large-scale datasets or pre-trained foundation policies. The research on lifelong learning agents focuses on transfer learning, domain adaptation, and imitation learning, highlighting the importance of understanding and leveraging task and domain relationships for improved generalizability. The authors emphasize the need for robust transfer learning methods, discussing optimal transport for domain adaptation and imitation learning strategies, including generative models and feature alignment. This research aims to advance lifelong learning agents by providing new insights and methodologies for improving adaptability and generalizability. Here is a combined summary of the 4 pages. Cross-domain imitation learning enables robots to learn from human demonstrations in one domain and apply this knowledge in another. The proposed method leverages reinforcement learning algorithms, such as proximal policy optimization, PPO, and domain adaptation techniques, like maximum mean discrepancy, MMD, to ensure learned policies are domain invariant. Generative models, specifically cycle-GAN, are employed to generate synthetic images from the target domain for training, reducing the need for real-world data collection and speeding up the learning process. Experiments on various robotic tasks, including object manipulation and navigation, demonstrate the method's superiority over baseline methods in terms of performance and efficiency. Moreover, the approach shows the ability to transfer skills between different robotic platforms, highlighting its versatility. The task adaptation algorithm is presented, where the state encoder and action decoder are trained using algorithm 1, leveraging a dataset for regulation. Results show a significant improvement in alignment scores using top 5 accuracy, as seen in Figure 7. The method is further evaluated on the ant-to-spider task, where the proposed approach outperforms others. The complexity of alignment is analyzed in terms of the number of demonstrations and proxy tasks, revealing a positive correlation with diminishing returns. The effect of increasing the number of source domains is investigated, showing a performance drop, especially when the number of domains increases without proportionally increasing the number of trajectories. The sensitivity of the performance to the MMD coefficient hyperparameter is also explored, with the proposed method showing moderate sensitivity. These findings contribute to a deeper understanding of lifelong learning agents and their adaptability in complex environments. The lifelong learning agent, PLP, is evaluated in various domains, including P2P medium, P2A medium, R2R lift, and V2V reach, demonstrating its ability to adapt to new tasks by aligning representations across domains. The relationship between the coefficient of the regularization term and success rate in PLP is explored, and the success rates of PLP with state input for the action decoder in R2R and V2V reach are compared to GAMMA's performance. In scenarios where actions from source domains are unavailable, PLP is extended to replace action prediction with next state prediction, decoupling the policy into next state prediction and inverse dynamics model. Although the results in Table 6 show limited performance compared to the original setting, the visualizations in the latent space of PLP demonstrate its successful adaptation to new tasks and environments. The paper presents visualizations of corresponding states in the latent space of PLP, showcasing the trajectories of agents in R2R lift and V2V reach. These visualizations highlight PLP's ability to adapt, while other agents struggle due to the lack of adaptation capability or finding exact correspondence between domains. The experiment details section outlines the environments used, based on D4RL, including point and ant agents, with varying state and action spaces. The tasks involve navigating through mazes with varying starting zones and goal locations. The authors employ the RoboSuite framework for R2R lift and the MetaWorld benchmark for V2V reach and V2V open, with different viewpoints employed for the source and target domains. Figures 13 and 14 display trajectories of agents in P2PUD and P2A medium, demonstrating the ability of the agents to adapt to new environments. The visualization results of the latent space in R2R lift using TSNE and the distributions of latent states in V2V reach reveal clusters formed by each ID, corresponding to different ball colors, in consistent positions across domains. The research paper discusses the lifelong learning of agents in various environments, focusing on the R2R lift and V2V reach tasks. In R2R lift, agents learn to navigate through rooms to reach goals, while in V2V reach, they learn to open or close windows. The authors introduce novel methods for representation alignment and out-of-distribution actions. They evaluate the success rates of proxy tasks and target tasks, showing promising results. The dataset includes state action trajectories of expert demonstrations across multiple tasks. For training, the authors employ a multi-layer perceptron (MLP) for the policy architecture and a convolutional network for visual inputs in V2V. The results demonstrate the effectiveness of their approach in lifelong learning, particularly in adapting to new tasks and environments. The authors employ a lifelong learning approach to tackle the problem of adapting to unseen goals in various environments. They propose a novel objective function that combines maximum mean discrepancy (MMD) and temporal contrastive coding (TCC) to align the representations across different domains. The MMD term ensures that the representations are domain invariant, while the TCC term captures the temporal relationships between states and actions. The authors use an AtomW optimizer with a learning rate of 5e4 and a batch size of 256 for the maze environments, and 1e4 and 512 for R2R lift, respectively. In the adaptation phase, the authors use about 400 trajectories towards an unseen goal to update the common policy for 50 epochs. They also mix the dataset for alignment to prevent domain-specific components from leaking into the common policy. Weight decay is used to stabilize the alignment and performance in P2P and P2A environments, with a coefficient of 1e5. A Gaussian kernel is used for MMD, with a bandwidth of 1 in all experiments. The authors also normalize the distance by the average pairwise distance in a batch to mitigate the issue of decreased representation scale. The authors evaluate their approach on various environments, including maze, R2R, and V2 volts, and compare it with baselines such as gamma, CDIL, and contextual. They re-implement the algorithms by referring to the original papers and official implementations, and sweep the hyperparameters to select the best performing models. The results show that their approach outperforms the baselines in most environments, demonstrating the effectiveness of the proposed objective function in adapting to unseen goals.